Okay, in this video, we're going to be doing Calc AB problem set number 129. The problems and a playlist are in the description below. Let's see what we're doing. Given that g of x is the integral from -2 to x of f of t dt, where the graph of f is shown above. Find g of -5. So first thing I'm going to do is just plug in. G of -5 should be the integral from -2 to -5 of f of t dt. But there's kind of a little problem there. We really want the upper bound to be the bigger number, and right now it's not. So I'm going to flip the bounds and change the sign and say that it's the negative of the integral from -5 to -2 of f of t dt. All right, now we got to do some geometry. So we're going from -5 to -2. So -5 to -3 gives us this region, which is a triangle, and then from -3 to -2 gives us that region, which is also a triangle. One is above, one is below. So it's 2 by -4 is -8 divided by 2. So we'll have -4, and then 1 by 2, but divided by 2 is 1. So we have the opposite of -4 plus 1, which is the opposite of -3. So 3 is our answer for g of -5. All right. On what intervals, if any, is g of x both increasing and concave up? And then we want to justify. So increasing, concave up. Increasing means the derivative of g prime is f of x. We got to get that down. So that's the second fundamental theorem. It's really f of x times 1 because the derivative of the upper bound is 1. All right, so we need g prime to be positive and we need g prime to be increasing because we want g to be increasing and concave up. So if g is increasing, g prime is positive. If g is concave up, g prime is increasing. So that's going to be this interval and this interval. So I'm just going to write that down. So that's from -3 to -2, and then also from 1 to 5. So I'm going to say g is increasing, concave up on -3 to -2, and 1 to 5, because g prime, which is f of x, is positive and increasing on those intervals. All right, let's take a look at the next problem. Given that h of x is x squared over g of x, find h prime of 3. All right, so we're going to start off by doing the quotient rule on this. So let's see. So h prime is going to be bottom, derivative of the top is 2x minus top, which is x squared. Derivative of the bottom is g prime, all over the bottom, g of x squared. Okay, now we got to figure out some values, right? I need to plug in 3. So h prime of 3 is just going to be 6 g of 3 minus 9 g prime of 3 all over g of 3 squared. So that's what we're doing. We need to know g of 3 and g prime of 3. So g of 3 going to be the integral from -2 to 3 of f of t dt, which again, geometry. So we got a triangle, which I think has an area of 3, and a triangle, which I think has an area of 1. So this is going to be 3 plus 1, which is 4. Then we need g prime, which we know is f of x. So we're finding g prime of 3 is the same as finding f of 3, which means just look at the y value on this graph. So that's here, it's 1. And now we got to plug everything in. So we are going to get 6 times 4 minus 9 times 1 all over 4 squared. So this is going to be 24 minus 9 over 16, which is 15 over 16. That's our answer. All right, let's take a look at the next one. Given that y equals f of x is the particular solution to the differential equation dy, I cut off the top of that there. dy dx is e to the y quantity 2x squared minus 4x. 2x, okay, yeah. For a second there, I thought you could combine those, and I was like, what am I even doing? Such that f of 4 is equal to 0. Right, the equation line tangent to f of x at x equals 4. All right, we need to know the slope. So dy dx when x equals 4, and at x equals 4, y is equal to 0. We need both because this is sort of an implicitly defined thing. It's got x's and y's. So it's going to be e to the 0 quantity 2 times 16 minus 16, which is just 16. So our tangent line, because we know the ordered pair is 4 comma 0, is going to be y minus 0 equals 16 times the quantity x minus 4. And just leave it. All right, part B, solve for f of x. All right, we're going to separate and integrate. So I'll get dy over e to the y. I'm going to write that as e to the negative y dy is equal to, and then the quantity 2x squared minus 4x dx. I should put integral signs, but I forgot to put them, as I often do. So, I mean, I guess I could, like, kind of fumble my way through it right now. They're not going to look good, though. Oh, man. Those are some bad integral signs. All right, we got this. So the integral of e to the negative y is negative e to the negative y. The integral on the right-hand side is just reversing the power rule. So we get 2/3 x cubed minus 4/2, or 2x squared, plus c. I think solving for c here is the easiest thing to do. It's only going to get more complicated. So I'm going to plug in 4 for x and 0 for y. So -1 is, you get 128 over 3 minus 32 plus c. If you do the math on that, you get that c is negative 35 over 3. All right, so now comes the somewhat challenging part. We have to solve for y. So the first step is I'm going to multiply everything by a negative, which just flips the sign of everything. I'm doing that because now I'm going to take the natural log of both sides. So if I take the natural log of both sides, I'm going to get negative y is the natural log of all of this stuff. I don't know why I'm making you watch me write that, but apparently I am. And then finally, I'm going to multiply through by a negative again. So I get negative natural log, absolute value, negative 2/3 x cubed plus 2x squared plus 35 over 3. It's a very gross answer, but I'm pretty sure that it's right. You can't balk at things like that. Like, it's going to happen. I mean, it's a weird-looking differential equation, so it probably has a weird-looking solution. Anyway, that's the entire problem set. I hope this was helpful, and good luck.